All right, these are problems 6 through 9 on review day 12. First one gives us a piecewise function, wants to know what's going on at 5, asking about continuity and differentiability. So we'll start with the continuous. We're going to throw 5 into the top part of it. We get negative 25 plus 3, which is negative 22. If we put 5 into the bottom part, we get negative 50 plus 28, we get negative 22. And it is defined at 5, so it is continuous. Okay, so f is continuous, f is continuous, f is not continuous, f is defined but neither continuous. All right, so we're down to a or b. And to see if it's differentiable, what we do is we take the derivative of both pieces, put 5 in, and see if the slopes now match. So on the top, the derivative is negative 2x. On the bottom, it's negative 10. If I throw 5 in there, I get negative 10, negative 10. Slopes match, so it is differentiable as well. All right, so check the continuity first, and if that checks out, then take the derivatives and see. The next one here gives us a derivative, tells us y is 1 when x is 1, and wants to know what would be an equation for y then. So first thing, when I looked at this, it's a little confusing because you can't really integrate. It's not a separable one, so we can't bring the y over and do stuff like we would normally do to this. Instead, what we need to do is just kind of take the information given to us. So if I throw 1 in for x, which one of these equations gives me 1 for y? So if I put it here, I get e to the 0, which is 1. 2 minus 1 would give me 1. That's okay. Same thing for b. But if I were to put 1 in here, 2 minus e to the negative 1, that's not 1. And same thing with d. So I can get rid of those. Those two do not do this first part. Okay? So now I got to figure out, well, which of these, if I take the derivative of it, would be 2 minus the original. Okay, so this is acting like y. Let me go ahead and take the derivative and see. So if I take the derivative on this one, this is 0. I'll get negative e to the x minus 1. That just repeats, and the derivative of that's 1. So the derivative, dy dx, of this one is negative e to the x minus 1. All right, so let me kind of set it up. Derivative, negative e to the x minus 1 equals 2 minus the original, which was 2 minus e to the x minus 1. So if I distribute that negative, I get 2 minus 2 plus e to the x minus 1. So I get positive e to the x minus 1 equals negative e to the x minus 1. That does not check out. If I do that same work for b, the derivative of that is negative e, and then the derivative of its exponent is negative 1, so that turns it into a positive. So the derivative of b is positive e to the 1 minus x. So derivative equals 2 minus the original. When I distribute the negative this time, I get 2 minus 2 plus e to the 1 minus x. And so I get positive 1 to the e minus x equals positive e to the 1. That checks out. Ugh. Real sneaky there. Not very obvious what we're kind of have to do on this one. There's a lot of different things you could do and spin your wheels on, but that's the route we want to take there. All right, number 8 gives us a function g of x equal to this. They want to know what's the x-coordinate of the point of inflection. So a point of inflection is when your second derivative switches signs. So what we want to do is get the second derivative going here. So g of x was this integral. So g prime would be the derivative of the integral, which cancels, and gives us x squared minus 5x minus 14. We'll just let the x drop in for the t's. So the second derivative then would be 2x minus 5. And if we set that equal to 0, we're going to get x equal to 5 halves. If we test both sides of it, one time it's positive, one time it's negative, and so for sure we have 5 halves as our point of inflection. Our last one here asked us to do the derivative of this. So it's a product rule to start with, and not a fun one at all with the secant in there. We got to remember what derivative secant was. So we'll start with the x cubed. Derivative of x cubed is 3x squared. Keep the secant as is. Plus, now we'll leave the x cubed as is, times the derivative of secant. Now, if you forgot what derivative of secant was, you could at least at this point say, okay, I knew it was product rule and I knew this part. So let me go take a look here. A didn't do product rule, so we can get rid of A, all right? B has the 3x squared secant x. It has the x cubed. Maybe B is right. If I look here, that one has the 3x, so, they all kind of have the x cubed. It's just a matter of knowing what that secant is. So I don't get any help there. Sometimes you can get away with it, right? And they kind of give you the answer without having to know all of it. But this one, they're not letting you off the hook. So you got to remember what derivative of secant is. So derivative of tangent is secant squared. The derivative of secant is secant tangent. Okay? I know Mr. Rudder has a kind of a neat way of remembering that. If you're in his class, maybe you had a little bit easier time with that than my class did. But whatever the case, derivative of secant is secant tangent. Now we're going to keep the 2x in there as is, and then we're going to multiply by the derivative of 2x, which is 2. All right, so now I'm looking, if I can put that 2 right here, I'm looking for something that has a 2x cubed secant 2x tangent 2x. 2x cubed secant 2x tangent 2x. That's option D right there.